Hello everyone. Welcome to the problem solving session number 10. So, for the course Hydraulic Engineering, which is being taken by the Professor Muhammad Saad Afzal in NPTEL. So, this is Dinchit Datta here. I am a research scholar at Indian Institute of Science, Bangalore. So, today I will be taking this session and let's get started. I hope you can hear me loud and clear. I will be turning off my video so that there is no bandwidth problem in between. So in this session we will be looking through the viscous flow and governing equations of viscous flow, that is a Navier-Stokes equation and its derivation, and we will also see some examples related to Navier-Stokes equations and that with analytical solution. See, one thing to remember is that the Navier-Stokes equation is not fully solvable every time. So only for certain cases and certain boundary conditions only you can solve it analytically. Else you will have to go for a numerical solution in most of the complicated cases. So before proceeding to the derivation, let us brush up some concepts that we have learned before. So first thing is the description of motion. So there are two descriptions. One is the Lagrangian description and other is the Eulerian description. So what do we do in a Lagrangian description? So in a Lagrangian description we follow a particle. So a particle will be moving, a fluid particle will be moving in fluid flow. So we will be following the particle and we will see how the properties of the particle are changing with time. And second, it's similar to like your so I can visualize it by the phenomenon. Suppose you were on a boat and in a moving river, so you are going with the flow and in the boat, so your velocity of the boat is almost equal to the velocity of the river. So you can, in that case, you are following the river and following the part like river, and whatever properties that you measure on the way, it will be in the Lagrangian frame of reference. The second is the Eulerian description. In this description, the fluid properties are described at a given point in space as a function of time. So it is like observer, the properties, how the properties are changing based on a fixed observer. So we have fixed one point in the fluid flow, and then we will see what are the properties that are changing with time at that point in the fluid flow. Then there is something called rate of deformation. It is similar to strain in solid mechanics. So the rate of deformation is given by suppose this is a 2D fluid element. Due to shear stresses on the fluid particle, fluid element has deformed by deformed. So to take a rhombus or parallelogram shape, so there will be a change in the angular deformation in both x as well as y. So this total angular deformation is will give the total angular rate of change of deformation is equal to the total angular deformation. So del alpha plus delta beta, and this comes out to be del v by del x plus del u by del y. U is the velocity x and v is the velocity in y direction. And okay, so this is one thing. And second thing is the angular velocity. We define the angular velocity omega as half of del v by del x minus del u by del y. So this is equal to del cross v. So it is the cross product of the velocity. So if this is the z direction, then the omega z will be curl of velocity, so it will only have the values with respect to x and del by with respect to y. So since the x and y planes are perpendicular to the z plane, so the angular velocity in z will have the values that the components that we define will be with respect to x and with respect to y, and the vorticity is defined as the 2 times the angular velocity. Okay, this is one thing. Then let us see through the definition of pressure in fluid dynamics. So when we talk about pressure in a fluid, so it is generally composed of 2 types. So one is the mechanical pressure and another is the thermodynamic pressure. So the mechanical pressure, it is the pressure that is acting normally to a surface of a control volume in a fluid. So you suppose this is a you can see the figure here. The vertical axis is the y, x is towards left and z is towards right. So you have taken a control volume that composes the origin and these 3 points. Suppose we mark it as A, B and C. So you got the control volume. So now suppose the fluid is flowing in all the 3 directions, suppose, then in that case, in this fluid element there will be some pressure force that will be acting on the surface AOB. So that is the normal pressure. Then there will be something that will be acting on the surface AOC, and that is be tangential to the surface. That will be the shear stress, and it is also the pressure arising due to the shear force. And similarly, there will be a pressure in the BOC plane, in this plane, again parallel to the in the tangential direction of the plane, and so this is the total force that will be acting in the direction of z, this z direction. Now so we define tau is, it is called the traction vector or also called the stress vector. So it is that there are 2 components in this vector. One is the I and another is j. So the j component, it signifies the direction of action of force. So if the force is acting on the z direction, then j will be in the z direction. And if and the first component I, it is a direction normal to surface. So if the suppose a force is acting, be it shear force or a normal force, it is acting on the surface. So the normal vector to the surface will correspond to the I component. Now so you have seen that in the surface AOB there will be one force tau 11, so that will be acting on the z direction, and similarly we will get one this is a normal stress in the AOC plane, and this will correspond to tau 22. Sorry, there is one mistake. So this is not x is towards this side and z is towards the. So tau 11 is corresponds to x direction. Now tau 33 will correspond to the z direction. So this is the total, the normal force, a normal pressure that is acting on the surface AOC. So this will be in the z direction. And thirdly, there will be a stress, let us put in this direction only, that will be a tau 2. So tau 22 will be in the y direction, correspond to y direction, normal. So the mechanical pressure is defined as the average of these three traction vectors, that is tau 11 plus tau 22 plus tau 33 by 3, and we take the negation. Why do we take the negation? In order to compensate for the change in value with distance. Sorry, no, this is not about change in distance, it is because of since these vectors are acting on the opposite directions to our convention, we have taken x to be positive on the right side, so the tau 11 is acting on the opposite, so it will be minus tau 11. Similarly, tau 33 is opposite to the z direction, so minus tau 33, and similarly tau 22 is acting on the opposite direction to our convention, so it will be minus tau 22. So the average of these three traction vectors will give the mechanical pressure. Now secondly, there is the thermodynamic pressure. How do we define thermodynamic pressure? It is defined as a pressure that arises due to the equation of state. Equation of state that relates pressure, density, and temperature. So you know that for ideal gas, there is an equation called PV equals to nRT. So this is for an ideal gas. So this is the equation of state for ideal gas, and here this pressure is the thermodynamic pressure. Similarly, for fluid, you can get it by based on the state of fluid, you can get an equation for thermodynamic equation for pressure. Now for our current study, we won't be differentiating thermodynamic pressure and the mechanical pressure. We will be considering both only one definition of pressure, that is that considering either thermodynamic or mechanical, we won't differentiate both. So with these assumptions, let us proceed to the Navier-Stokes equation and derivation. So now the thing is that we have seen before, like while deriving the Euler equation and the derivation of equations of motion, if we take a control volume like cubical control volume in a fluid, then and if u, v and w are the velocities in x, y and z direction, and tau x is tau y, and tau are the shear stresses in x, y and z, then we will get equation of motion that will be given by this formula, well, del by del t of rho ui plus del by del x. This is the local acceleration, force due to local acceleration, and this is the convective. Then del by del x of tau ij plus rho bi. Rho bi is the body force, and this is the rate of change of this is the gradient of the traction vector. So this component tau ij will have both the normal pressure as well as the shear stresses, force due to shear stress, both the factors it has inside it. So this tau ij it depends on the rate of deformation. Now which component is contributing to deformation? So there are two components that we already said. One is the normal force, another is the shear force. The normal force won't be causing any deformation in the fluid. Only the shear force that is acting tangentially will be causing deformation in the fluid element. So how do we do? We do use the law of superposition, and we Now break the equation like tau ij into two parts. One is tau ij hydrostatic and the other is the tau ij deviatoric. The deviatoric part will contribute to deformation and the hydrostatic part will only contribute to net volume change. So it is like you are pressing the fluid in all the directions, so it will have, if the fluid is compressible, then there will be change in volume of the fluid, but if this fluid is incompressible, then there won't be any change in the volume of the fluid. I hope these two factors are clear. How we have divided the tau ij equation into two parts. Wait a minute, continuing. Now we will see the rate of deformation. It is given by del ui by del x. So I corresponds to x direction and j corresponds to y direction. So this is a symmetric tensor. So we can break that into two parts, into one asymmetric sum of a asymmetric and a symmetric tensor part. So we have broken this del ui by del xj into two parts by adding and subtracting del uj by del xi, and we got two components, half of del ui by del xj plus del uj by del xi plus half of del uj I by del xj plus minus of del uj by del xi. So the first part is called the, will contribute to deformation. It is called the rate of deformation tensor. Okay, sorry. So I was talking about rate of deformation. So how we define rate of deformation? So it is del ui by del xj. So I corresponds to the velocity, ui corresponds to velocity in x direction, or I direction, and xj corresponds to the rate of change in y direction. So you can change ui, I and j corresponding for different x, y and z direction. Now this rate of deformation tensor, it can be divided into like routine as a sum of two parts. One is a symmetric part, another is the asymmetric part. Symmetric part, and another is the asymmetric part. Now, so how do you write? We just add and subtract the terms del uj by del xi, and we will get two tensors. One is the deformation tensor and another is the rotation tensor, rotation vector. Now we have what we have defined. We told that we seen that the tau is a deviatoric shear stress will depend only on the rate of deformation. So it will only depend on this part. Okay, so till now it is, hope it is clear. So we'll now proceed to our definition. So when you're talking about a Navier-Stokes equation, so there are two tests, the Navier and Stokes. So the first thing that we consider is a Newtonian fluid. So this Navier-Stokes equation is valid for a Newtonian fluid, and then after going to this derivation, we will see how we assume the Stokesian hypothesis to correspond for the derivation of the equation. The first thing is then tau ij. The tau ij is a second order tensor. So it, because since there are only two terms, I and j, and it depends on the deformation tensor E epsilon kl. Deformation tensor, and it also has only two components. Now for a Newtonian fluid, what happens is this: the a second order tensor can be related to other second order tensor by a fourth order tensor. So let us define this for fourth order tensor asCijkl. So thisCijkl will have 3 to the power 4 components, since each of the component I, j, k and l will have 3 degree of freedom for each of I, j, k and l. So if there are 3 degree of freedom, so there will be total 3 to the power 4 components. But we have seen that the shear stress, the deviative shear stress, is a symmetric tensor. Symmetric means what? The tau ij is equal to tau j I. So in that case, this number of components will be reduced to only 36 components. Okay, so after this, what we consider? So now but still solving for 36 components is again a very complicated case. So there will be a large number of terms. So again, to reduce the number of components, we consider a homogeneous and a isotropic fluid. So what do you mean by homogeneous fluid? A homogeneous fluid is where the fluid properties are independent of position. So at whatever position you measure the properties, it will be same. And isotropic fluid is what? A fluid that is independent of direction. So you proceed in x direction or proceed in z direction, the properties of the fluid won't be changing. Okay, so yeah, so these are two conditions. Now we need to get a scalar based on theCijkl. So if we to get a scalar from the componentCijkl, we multiply with, take the dot product with 4 components, that is Ai, Bj, Ck and Df. If we take the dot product with these 4 terms, we will get a scalar vector or a scalar, and let us assume this scalar is given by this, that is alpha into A dot B, C dot D plus beta into A dot C, D dot D, and gamma into A dot D into B dot C. Now we will define something called the Kronecker delta. Kronecker delta, it is just to make our computations easy and convenient. We use this thing called Kronecker delta. It is defined as delta ij, and delta ij is equal to 1 if I is equal to j, and it is 0 if I is not equal to j. Now there is one property of delta ij, that if you suppose multiply a vector bi with delta I into j, you will get beta in b of j. This property will be very useful in our derivation, since we are using the vector notation. So yeah, so we have assumed thatCijkl is into aib, j, ck and dl. It can be written in terms of this. So what we will do, we will write these terms with terms of Kronecker delta. So we get alpha into ai bj ck dl into delta ij into delta kl. How do we get that? Okay. So a dot b is I dot bj into delta ij. So if I is equal to j, this three terms comes from the a dot b. So if I is equal to j, then it will be ai into bi, so there will be a term. If I is not equal to j, then this term will go to 0. So this is the property of dot product. I think you know till now, since we have read vector calculus. Similarly, we write c dot d into equal to ck into dl into delta kl. So similarly, we expand all the terms. So now if we expand, now we can cancel ai bj ck dl from both sides. So c I j k l, that is the tensor, is given by alpha into delta ij, delta kl, delta ik, delta jl plus gamma into delta il into delta jk. Now we considered one more factor, that is symmetry, that is tau ij is equal to tau ji. So in that case, what will happen? We can write c I j k l is equal to c j I k l. So now if we substitute the j in terms of I, that is like interchange j and I, we will get Cijkl, and if you equate both the Cijkl and Cjikl, then in that case the first term will vanish. Alpha delta ij and alpha delta ji will vanish. Now only two terms will remain. One is beta into delta ik into delta jl, and minus of gamma into delta il into delta jk into delta il. So now this term cannot be 0. So this is the arbitrary part. So for this term to be 0 always, so this term should be 0. So beta is equals to gamma. This is what we got. Now we will substitute this in the main equation. So if we substitute, we will get Cijkl, this term for Cijkl. Okay, so we got, now we substitute in the main equation, that is for tau ij. So it is epsilon Cijkl into epsilon kl. So alpha into delta ij into delta kl into epsilon kl. Similarly, beta and delta ik, delta jl into epsilon kl, and gamma into delta L jk into epsilon k. For repeating indices of epsilon or deformation tensor, we will get something called epsilon kk, and let us write the terms. It will be epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3. And taking the summation of expanding the terms and then taking summation, you will get finally del u1 by del x1 plus del u2 by del x2 plus del u3 by del x3, and this is nothing other than the continuity equation. Okay, now what we have seen that, yeah, so if we combine these terms, like when taking multiplication delta KL into epsilon KL, similarly and that's product of these three terms also. So we have seen that if you multiply, suppose delta JL into epsilon KL, what we will get? We will get epsilon JL. Now if you multiply that with epsilon I, epsilon JK, sorry, you remove the repeating index. You will remove and now if you multiply that with epsilon delta ik, you will get epsilon I j. So repeating index will be removed. So this term will come as epsilon j, but here after multiplying we will get epsilon kk or epsilon ll, and it is multiplied by delta ij, so if this term will remain like that. So after simplification we will get the expression for tau ij deviatric as alpha into delta ij into epsilon kk plus beta e epsilon ij plus beta epsilon ij. So it will be 2 beta epsilon ij, since these two are symmetric. So now what we define based on experiments, what the scientist has done by Navier and Stokes, it is found that the alpha, it corresponds to the second coefficient of viscosity. It is denoted by the symbol lambda, and beta, it comes out to be the dynamic viscosity of the fluid. So it is denoted by mu. So this is for tau ij deviatric. Now tau ij hydrostatic, it is again only to the normal forces. So the normal forces will corresponds to only P into delta ij. So if I equals to j, then it is equal to minus P, else it is 0. So the total or the net fraction vector or the net force is given by tau ij hydrostatic and summation of the hydrostatic and the deviatric term. So what we get? We will get minus of P delta ij plus lambda epsilon kk in delta ij plus 2 mu into E ij. So we will expand this term in all the three directions. First we write in terms of x, next y, and thirdly z. If we write in the direction of x, then tau 1 1 is equal to minus P plus lambda del uk by del xk plus 2 mu into del u1 by del x1. this is for when I equals to 1, j equals to 1, when I is equals to 2, j is equals to 2. So we are taking equal values of I and j and then expanding the terms. So if we then take the summation and the average, what we will get? We will get tau 1 1 plus tau 2 2 plus tau 3 3 by 3 is equal to minus p plus lambda plus 2 by 3 mu into del uk by del x cube. Now, as per definition, this first term corresponds to the mechanical pressure, and the second term that arises, that minus p, it corresponds to thermodynamic pressure. But we have decided that we will be considering, we won't distinguish between mechanical and thermodynamic pressure, so we will be considering both the values to be equal. And this comes from the Stokesian hypothesis. He told that the mechanical pressure and the thermodynamic pressure are equal. So in order to validate this hypothesis, what will be the cause? What will be effect? So effect will be the third term, that is, this must be equal to 0. If this is equal to 0, then del uk by del xk is not 0 always. So the other term, that is the lambda plus 2 by 3 mu, is equals to 0. So the value of lambda is equal to minus 2 by 3 mu. Now there can be three cases where the this hypothesis is valid. One is like when for dilute monoatomic gases. In that case, there is only one direction, one degree of freedom, that is translational degree of freedom. So the thermodynamic pressure is equal to mechanical pressure automatically. Then secondly, if we take incompressible flow, that is incompressible flow, del dot v is equal to 0. So this term is equal to 0 for incompressible. In that case, we need not consider the Stokesian hypothesis. So in that case, the Pm will be equal to the thermodynamic pressure naturally. And the third case is when the Stokesian hypothesis works, is like when a time scale of change, that is greater than the relaxation scale. So when the parameter or the values are changing at such a rate such that it is greater than the relaxation scale, in that case the Stokesian hypothesis is valid. So we got the equation for tau ij. So we can now substitute in the main equation, that is the first equation that we wrote. So the left hand side will remain intact, the del by del t of rho ui plus del by del xj and rho uj and ui. The second term, the right hand side, so in the right hand side the first term will be, we have to expand the first term. So it will be minus of p delta ij plus lambda del u by del ur by del xr into delta ij, and thirdly there is this 2 mu into eij. So eij corresponds to del ui by del xj plus del uj by del xr, and lastly there is this body force. So after expanding the terms, what we will get? We will get minus del p by del xi, since del by del xj is multiplied by delta ij, so only ith term will remain. Plus del by del xi into del u del lambda into del uk by del xk. So this is comes second term, and then the third term and the fourth term. So one is mu into del by del xj del ui by del xj, and the next term is mu into del by del xj del uj by del xi. Now here this term we can write, instead of we can take del by del xj inside and del by del xi outside. So it will come as del by del xi into mu of del uj by del xj, and del uj by del xj can be similar to del uk by del xk. So this one depend on the vector notation. So the total you get, finally again rearranging the terms, we will get first term will be remain like that, last term will be remain like that. Instead of the second and the fourth term are combined to get lambda plus u into del uk by del xk, and rate of change with respect to del by del xi, and the fourth term will be third term will remain intact, that is del by del xi into mu of del ui by del xj. Now substitute using lambda is equal to minus 2 by 3 mu. So if you substitute, you will get this equation. So this equation, it is valid, it is called a Navier-Stokes equation, along with the continuity equation. This is valid for a homogeneous and isotropic fluid, and where it is for fluid is Newtonian, and also it follows the Stokesian hypothesis. So the Navier-Stokes equation can be written in two forms. One is a non-conservative form and other is the conservative form. So how do we write a non-conservative form? The non-conservative form can be written as ui into del rho by del t. The left hand side will remain intact. Oh no, we will expand the left hand side. That is ui del rho by del t plus rho del ui by del t, and ui del rho uj by del xj plus rho ui into rho uj into del ui by del xj. So we can combine del ui by del t plus rho uj into del uj by del ui by del xj. This will give rise to the continuity equation. So the sum of these two terms will be 0. So what will remain? It will, the other terms will be remaining. Sorry, not the last term, first term and the second term and the third term. So the first term will be remaining like this, and the last term will be remain. This will vanish from the continuity equation. So and then finally we can write this as in terms of material derivative, is rho into du by dt. So we have written this. Now substitute this in the main equation. We will get rho into du by dt minus of del p by del xi plus mu del by del xi into mu by 3. This term will also go to 0 since we have considered continuity equation. This term will go to 0 when flow is incompressible. When the fluid is not incompressible, then this term won't be 0, and the other terms will remain like that. So this is called the non-conservative form of the Navier-Stokes equation. Since we have removed the conservation of continuity like mass from the equation, so it is called the non-conservative form. If we don't remove this continuity equation, then it is called the conservative form. And now the same equation for incompressible flow, it is same. This term will go to 0, so only the first this term will remain, then rho bj will, rho bx will remain, and this term will be remain. So at the same equation we can write in terms of vector, that is rho into du by dt is equal to minus of del dot p minus of grad of p plus rho into b bar, where b bar, where b, this is the body force, and mu into del square. This comes from the viscous terms or the shear force. So this is the Navier-Stokes equation simplified for incompressible flow. If there are any doubts till now, you can ask. Hello. Class চলি আছে মোৰ পিছত কৰিম নেকি? Okay. Okay, now we'll see two examples. Okay. Now we will see two examples of Navier-Stokes equation, like where you can have the analytical solution. First thing is we will consider a flow between parallel plates where both the plates are fixed. So these are two parallel plates. So if we consider a steady flow, that is the velocity is not changing with time, a boundary layer will be forming, and the velocity distribution will be somehow like this. So in that case, as the flow is taking place, the u2 is greater than u1, that is a section 2, the velocity will be higher since the boundary layer region is increasing, so the core region flow will be taking place through a smaller area, so higher velocity in that region, and there will be lower velocity in the first region since it is has more area, so the pressure is less and the velocity is also less. Now on a fully developed flow, the boundary layers have vanished and we get a fully developed flow. In that case, after a fully developed, what we see that the rate of change of u with x is 0, that is we consider uniform flow, and the rate of change of velocity, that is vertical velocity with respect to y, is also 0. So this gives v equals to 0. And how this will come? This will come from the continuity equation. So we get del v by del y equals to del u by del x equal to 0. So we will substitute these terms in the Navier-Stokes equation. So first we will write a Navier-Stokes in the y direction. So we will cancel the terms that are in 0. So what we will get finally, we will get del p by del y is equals to minus of rho g. So p is equals to minus of rho gy plus f of x. Now secondly, there is a Navier-Stokes in the x direction. Here again del u by del x is equal to 0, del u by del y is not equal to 0, so that term will remain, and the other terms del square u by del x square is equal to 0, okay, and del u square by del square u by del y square will also remain. So we get the final equation as mu into del square u by del x del y square is equal to dp star by and this term will be 0 since v is equal to 0. So what we consider p star as fx plus rho gh. So you will get this equation, and finally we get the velocity of u with respect to average velocity as 3 by 2 into 1 minus y square by h square. So this is the equation of the flow that we obtained. Similarly, there can be another type of flow. It is this type of flow is called the plane Poisson flow. Similarly, there is also another type of flow. It is called the Coute flow. Coute flow. So here, what we take that velocity, the upper plate is moving at a velocity u. So this, if we consider this is a shear driven flow, since the upper plate is moving, so the governing equation will be same here, that is mu over d square u by dy square equal to dp star by dx. Only the boundary conditions will be changing. So how will we change the boundary conditions? Now at y equals to 0, at y equals to 0, u is equal to 0, since this comes from a no slip condition, since the lower plate is at rest. At y is equal to h, u is equal to ut. This is because at the top plate is moving at the velocity ut, so the fluid particles attached to that plate will also be moving in the same velocity. So if we substitute, we will get a general solution as u into is equal to 1 by 2 mu into del p by del x plus y square plus c1 y plus c2. Now, so if you substitute the first boundary condition, you will get c1 is equals to 0. Sorry, c2 is equals to 0. Now, and after substituting that, we will substitute the second boundary condition at y is equal to h. We will get c1 is equals to ut by h minus 1 by 2 mu into del p by del x into h. So this is the, now we substitute c1 and c2 in the main equation, and finally by rearranging the terms we will get this equation. So the u with respect to the u top on the plate is y by h minus h square by 2 mu ut into del p by del x into y by h minus y square by h square. So we define a non-dimensional pressure term called P star, which is given by minus of h square by 2 mu into del P by del x. So this will come as this formula. So there can be three cases, so we will consider the cases. Now if we consider a simple shear flow, in that case we do not consider any pressure gradient in a direction of the flow, that is P star is equals to 0. If there is no direct pressure in the direction of flow, then P star is equal to 0. So ut by u is equals to y by h. So this can be produced by sliding the parallel plate at a constant speed relative to the stationary wall. And then the second condition is P star is less than 0, that is there is a positive pressure gradient, the negative pressure gradient. So in positive pressure gradients, so del P by del x is greater than 0, or is also called the adverse pressure gradient, and say this will cause u by ut is less than 0. So the direction of velocity of flow will be different to that of the velocity of the wall, that is the moving wall, top plate. So in that case, the fluid motion created by the top plate won't be strong enough to overcome the adverse pressure gradient. So in this case, there will be a backflow in the lower region. So the velocity will be negative in this lower region and positive in the upper region. And the third case, P star is greater than 0. If P star is greater than 0, then the fluid motion of the top plate is enough to overcome the adverse pressure gradient. since here del p by del x ut will be greater than 0 at some point between the two plates. So now let us find the maximum and the minimum velocity for the two conditions. So for either maximum or minimum, we should differentiate u with respect to y, and this is equals to 0. If del u by del y is equal to 0 and we differentiate, we will get this term ut by h plus p star ut by h into 1 minus 2 into y by h. And if we equate this to 0, we will get ut by h will get cancelled. So we will get a relationship of y by h, that is the location of maximum velocity or the minimum velocity with respect to p star. So now based on the value of p star, we will have different value of y. So at p star is equal to 1, what will happen? When p star is equal to 1, then the maximum velocity occurs at y by h equal to 1. So at is it will occur at the location of top plate. The second case is p star is greater than 1. When p star is greater than 1, this term will be less than 1, but it will be greater than half. So in that case, the maximum will occur at some location below the plate, but will be greater than h by 2. Now the third case is when p star is equals to minus 1. When p star is equals to minus 1, if you substitute here, then half minus half will go to 0. So the minimum velocity will be occurring at y by h equals to 0, that is at the location of bottom plate. And lastly, when p star is less than minus 1, then the maximum velocity will occur at a velocity of y by h greater than 1, that is outside the location of plate, and the minimum velocity will occur at a location y by h less than half. So the minimum will occur somewhere in the lower half. So this is one condition. So in between p equal to minus 1 to p equals to 1, there will be in that case there will be the maximum point of maximum velocity will be varying from 0 to h. So I hope you understood this. So now if we can find the values will be like this. For p greater than equals to 1, u max by ut is equal to 1 plus p star whole square by 4 p star, and p less than minus 1 equals to u mean by ut is equal to 1 plus p star whole square by 4 p star. And if we relate the average velocity with the discharge q, then at p star is equals to minus 3, we will get q and u average equals to 0. So just remember this derivation, you will get some questions. Okay, we will now see through some questions. The first question is, in a viscous fluid flow, the Hagen-Poiseuille formula represents, what does it represent? It represents pressure drop. The formula is P1 minus P2 by rho g is equals to 32 into mu v L by. So this represents pressure drop. The second question is the ratio of maximum velocity to average velocity of a viscous fluid flow between parallel plates. So this formula is given by u bar is equal to 3 by 2. So I have derived this in one of my previous lecture while studying laminar flow. You can go through that and you will see the derivation. The fluid in a nozzle where the velocity field is function of position and time. This description represents Eulerian description. Right? In Eulerian we define a position where we are measuring the velocity values, and then at that position with different time intervals what the values of velocity that we are, or the parameters that we are getting. Now the Navier-Stokes equation is derived from the Newton's second law. So it uses the second law of motion in term for a fluid. That is, based the force acting on the fluid element is translated into in terms of body force, shear force, and viscous force. Now stress tensor tau ij is a symmetric tensor. We have seen that tau ij is equals to tau j I. And there is question 7. It says the vorticity in a z direction is given by, so omega z is equals to x minus of del u by del u. We have seen this. Okay, this is the question on a streamline. To get the equation of streamline, we need to get the equation slope. The slope will be given as dy by dx. It will be equals to v by u is equal to y into 1 plus t by x plus 2t. Now holding time t constant, we can separate the variables. So we consider t is equals to constant, and now we can use the variable separable form. This will come as c into ln x. So y is equals to e into x to the power c. Now to satisfy initial condition, y naught is equals to p into x naught to the power of c. Therefore the equation of streamline is y by y naught is equals to where n is equals to 1 plus 3 by 1 plus 3. Answer is option C. So now we have to find shear strain. Take epsilon x is equal to half into so this is equals to half into del v by del x will be 10x square y by del x, so 20xy minus and del like u by del y is equals to 0. The volume rate of flow q between the streamlines phi 1 and phi 2. If there are two streamlines psi 1 and psi 2, then the volume rate of flow q is given as psi 1 to psi 2 is equals to psi 2 minus of psi 1. Correct answer is option C. This is a bit of a typical question. A solid cylinder of mass m, radius r and length l falls concentrically through a vertical tube of radius r plus delta r, where delta r is less than or equal to r. The tube is filled with gas of viscosity P and mean free path L. Neglect fluid forces on the front and back faces of the cylinder. And consider only shear stress in the annular region, assuming a linear velocity profile. Find the analytic expression for the terminal velocity of fall V of the cylinder for no slip and with slip. So this is the diagram of a cylinder, and this is the layer of tube. So this is R and this is so there is a fluid of shear stress. The velocity profile is linear. Okay. Now at this surface so if we take the frame of reference with respect to the cylinder, we will get this surface is static and this outer layer is moving. So due to no slip condition, the velocity of the gas at the surface of the cylinder will be 0. Now the drag force is given by the shear force. So the shear stress over the surface area of the cylinder is 2 pi RL into integration of tau dr. So we replace tau by dv by mu into dv by dr. So mu is equals to p. So we get the final drag force. This is drag force 2 pi RL into p into v by r. Now this drag force is balanced by mg to get terminal velocity. So therefore mg is equals to 2 pi RL p into v by r. Therefore v no slip will be given as mgr mg by 2 pi L into p. This is for the no slip condition. Now we will see how it will be for the slip condition. Now for the slip condition, what we have, the velocity at the surface of cylinder is not equals to 0. In that case, the velocity of the surface is given as lambda into dv by dy, where lambda is the slip coefficient and it depends on the properties of the gas. And the effective viscosity in the fluid is given as P into P divided by 1 plus lambda by L, where L is the mean free path. So using the same procedure, we can use the drag coefficient Fd is equals to 2 pi RL into eta effective into V by R. So equating with mg, so mg equals to, and eta effective is given by 1 plus lambda by L. If you get the appropriate values of lambda, you will get mg into R plus 2L by 2 pi RL. the viscous force negative motion between the adjacent layers of fluid motion which one of it opposes the fluid motion. So let us try some questions from GATE. So let us consider a laminar flow with zero incidence over a flat plate. The shear stress at the wall is denoted by EW. The axial position x1 and x2 on the plate are measured from the leading edge in the direction of flow. If x2 is greater than x1, then the shear stress at x1 should be less than shear stress at x2. Let us see. So this is one location and this is other location. So this is the growth of boundary layer. This is x1. So now 1 is equals to the Laplace's equation denotes that the shear force is 0.664 by root REX, and this can also be written in terms of tau W by half delta U infinity square. So if we equate both, you will get a relation between tau W and x. So tau W is equals to 1 by root x. So for x2 greater than x1, so tau W x1 is greater than tau W x2. So there is a second question. For steady flow in a viscous incompressible fluid through a pipe in a constant diameter, the average velocity in the fully developed flow is constant. Which one of the following statements about the average velocity in the developing region is? Now the average velocity is constant. So the discharge is constant and area is constant. The discharge is constant. Then in the boundary region also the same amount of discharge will be flowing through the same layer. So it is constant is equal to average velocity in the fully developed region. So water is flowing through a horizontal pipe of constant diameter, and the flow in the laminar flows. The diameter of the pipe is increased by 50%, keeping the volume flow rate constant and the pressure drop due to friction. So delta P due to friction is given by this Hagen-Poiseuille formula, 32 mu V L by a square. So if we write in terms of diameter and Q, it will be 28 mu Q L by pi d to the power 4. So for lambda, for diameter 1, delta P1 is C by d to the power 4, and for diameter 2, delta P2 is equal to C by d2 to the power 4. Now d2 is given as 1.5 d, it is increased by 0.5 d. So the pressure drop will be delta P1 minus delta P2 by delta P2. If you substitute, you will get 80%. So how do you it will be? So see where you can cancel these terms. So 1.5 to the power 4. So we will get around 15 to the power 4. It is coming around 5.06. So 50%. So this is all about today's class. If you have any doubts, you can ask me, else we will end the session. Okay, so we'll end today's session here. So have a nice day. Good night.